Welcome back, everybody. Section 5.1, Inverse Trigonometric Functions, Part 2. We're actually going to get into the inverse part today. Now, if you haven't done the homework for Part 1 yet, if you haven't practiced that, pause this video, go do that. Go get through homework 1 through 7. Okay, because what we're doing today builds right off that, so you want to practice first. Okay, otherwise, let's rock and roll. Let's get going with Part 2. So talking inverses, and here are the definitions for the three inverse trig functions we're going to use. Kind of looks like yuck, but let's go through these. So let's talk about sine inverse first. I'm going to say sine inverse of x, or arc sine, is the unique angle y between negative pi over 2 and 2, such that sine of y equals x. Okay. So in other words, if I want to know what the sine inverse of x is, I need to figure out what value y, in other words, what angle makes the sine function equal to that x. In other words, I need to solve this trig equation. Okay, now with our simple trig equations, we looked at restricting them to parts of the coordinate system so we'd have a single solution. Now same thing here with the sine. I want that y to be between negative pi over 2 and pi over 2. I'll show you why that is in a second here. Okay, cosine inverse, same idea. The cosine inverse, or arc cosine, the two of those mean the same thing. This would be the way you type it into a computer just because it's hard to program with superscripts like that. Okay, is the unique angle y between 0 and pi such that cosine y equals x? So in other words, cosine inverse of x is equal to the angle y such that cosine of y equals x. So in other words, solve this trig equation. And again, we'll restrict that to 0 and pi. Okay, same idea with the tangent. Tangent inverse, or arc tangent of x, is the unique angle y between negative pi over 2 and pi over 2 such that tangent of y equals x. In other words, if I want to know what the tangent inverse of x is, I figure out what y, I plug into the tangent function to get that x out. Okay, again, we're solving simple trig equations here. Okay, things to notice the sine and the tangent have the same restrictions on their domains, we could say. Whereas the cosine inverse is different. Okay, sine and tangent are negative pi over 2 to pi over 2. Cosine is 0 to pi. Okay, so we've got our formal definitions. I like to compact that into kind of a tighter set of formulas and then also think about it visually. Okay, so again, sine inverse of x equals y means the same thing as sine of y equals x. Okay, that's how we defined inverses for you way back in first semester. Basically, the x and y's flip. So again, if I want to know what the sine inverse of x is equal to, well, I need to figure out the sine of what equals that x. And we can do the same thing with our definitions of cosine inverse and tangent inverse. Okay, now as far as remembering what their restrictions are, I like to think of that visually. Okay, my sine inverse and tangent inverse are restricted from pi over 2 to this negative pi over 2 here, whereas the cosine inverse is restricted from 0 to pi up top. Whoops, I should have a negative pi over 2. That disappeared from my picture somehow. Okay, so I like to keep that picture in my mind for the restrictions. Right, next thing I want to talk about real quick is why we need these restrictions and why they are what they are for our different functions. So basically we need these restrictions to make the sine inverse, cosine inverse, and tangent inverse actually functions. So here's what I've got for you. I've got an angle and standard position that I can rotate around. And then on the left side what I have is I have the inverse of right now my sine function being graphed. So I'm flipping the x and y's. Instead of the angles on the x-axis and the trig values on the y-axis, I have those flipped around. Y-axis has the angles I get out. X-axis has the trig values. And if I don't restrict my sine inverse as I draw this guy, notice I get something that's not a function. This would not pass the vertical line test. There's overlap. So what I want to do is I want to come up with a set of restrictions that allows me to get all the possible sine values out from -1 to 1 without any overlap. Okay, to do that, I'm going to go up to pi over 2. And the trick is to make this unbroken. I'm going to back things up to, that says 3 pi over 2, negative pi over 2, same thing. Okay, so when I restrict myself to this range, I get from -1 to 1. okay, without any overlap. Okay, if I do the same thing with arc cosine, so now I'm graphing the cosine flipped sideways, the same restrictions don't give me a function. So what I need to do to make the arc cosine work to get all the way from 1 to -1 is just go from 0 to pi. Okay, tangent inverse, arc tangent, same thing. I could do it that way, but it's broken. Okay, if I restrict that from, again, -pi/2, pi/2, I see I cover this entire graph from -infinity to infinity without any overlap. If I start going beyond that, okay, that's when I get the overlap. That's when I get, okay, something that's not a function. All right, so after all that, let's jump into the problems finally. Okay, a lot going on in the background, but these problems actually aren't that bad. Problem 3, part A says, find the exact value of the inverse. Okay, figure out what tangent inverse of -√3 is equal to. Okay, well, to do that, we're basically going to turn this into a trig equation. So let's say that tangent inverse of -√3 is equal to some number x that we're trying to find. Now, what that means based on our definition is that means that the regular tangent of x is equal to -√3. So again, really what we're doing is just solving a simple trig equation from our last video, from the last part of this section. Okay, a couple things about that. When I see that -√3, I can think of that as a -√3 over 1. That's going to help me think of this in terms of opposite and adjacent sides. And then earlier when we were solving these simple trig equations, we always gave you restrictions on where my solution, where my angle could be. Okay, because we wanted one solution rather than the infinite number of them. Okay, well, with our inverses, those restrictions are given to us. We said that tangent inverse happens somewhere between -pi/2 and pi/2. Okay, so when you go to solve this trig equation, your restrictions are given based on what type of inverse you're looking at. Okay, from there, I want to figure out what value gives me this -√3 over 1. Well, everything's positive in the first quadrant, so I know that's got to be in the fourth quadrant here. And my angle is going to be opening down, not up. Okay, because this angle here would be too big. That'd be greater than pi/2. So I want the one that's opening down to be greater than -pi/2. Okay, tangent, like we said, is opposite over adjacent. So my opposite side is the -√3. The adjacent would be the 1. Hypotenuse is 2. Looks like we're looking at my 30, 60, 90 right triangle. So I could say then my x, or I could say that my tangent inverse of -√3 is equal to -60 degrees, all right, or -pi/3. I think this is what's in the answer key. That's probably what's going to be the way we want on the quiz. Okay, so that's just converting -60 to -pi/3. Okay, so solving an inverse is really just the same thing as solving a simple trig equations with some restrictions given based on the definition of that inverse. All right, part B is the same idea, and part C is actually a special case of this that we already talked about in the previous video. Why don't you pause right now, give part B and C a shot, and then hit play to check your answer. All right, part B. We want to know what the cosine inverse of -√2 over 2 is equal to. Let's say it's equal to some number x. And saying this means the same thing as the regular cosine of x is equal to -√2 over 2. Okay, so when I'm asking what's the value of an inverse, what I'm asking for is what is that angle that gives me, all right, this ratio out. Okay, so we have a simple trig equation, and I suppose like usual when I see this √2 over 2, I know that's the same thing as cosine x equals -1 over √2, if I kind of unrationalize it. So simple trig equation, we'll go to our angles in standard position. And the restrictions we put on our cosine inverse, we said cosine inverse is restricted from 0 to pi. Okay, so I know I'm looking for a solution somewhere in the first or second quadrant with this one. And since we want a negative answer, I know we're talking second quadrant. Again, everything's positive in the first. We're talking cosine, so that means that the adjacent side's 1, hypotenuse is root 2. So we've got our negative 1 here, root 2. Okay, this is the 1, 1, root 2, 45, 45, 90 right triangle. Okay, then the angle I'm talking about is actually this angle here in standard position, which is going to be 180 degrees minus 45. Okay, because we're 45 short of the 180 line here. So in other words, we're talking 135 degrees. Okay, so I could say that cosine inverse of negative root 2 over 2 is equal to 135. All right, or if I convert that, I know I have a 3 pi over 4. And I can do that quickly because I know 45 degrees is pi over 4, and I'm pi over short of pi. Okay, so that's where we're getting that 3 pi over 4. All right, like I said, C is a special case of this that we dealt with in the last video. So we want to know what the sine inverse of 1 is. We'll say that's some value x. And what that means is sine of x is equal to 1. Okay, we want to know what the sine inverse of 1 is. Then we want to know what angle I plug into sine to give me the 1. And like we talked about in the last video, when I have nice values that my functions are equal to, like 1, negative 1, or 0, it's going to be easiest to solve these trig equations using a graph of the function, okay, rather than angles in standard position. Because what we're talking about here is a coterminal angle, and I think it's easier to do these this way. So let's graph my sine wave. It runs between 1 and negative 1. Okay, I want to know where it's equal to 1, so I'm talking about this point right here. So I want to know what x value I have. In other words, I want to figure out what this x is. Well, I know sine completes a wave after 2 pi units. So half of it's going to be pi units. So pi over 2 is going to be the angle I'm looking for here. All right, because sine of pi over 2 equals 1. And I suppose as far as restrictions go, we said that the sine inverse was restricted between negative pi over 2 and pi over 2. So I'm just looking at this chunk of the graph. Again, pi over 2 is going to be what gets it done here. So we can say sine inverse of 1 is equal to pi over 2. All right, the last thing we're going to do is look at the composition of trig functions and inverses. Okay, remember, a composition of functions is basically where I take one function and place it inside of another one. So as you can see here, I've got a cosine function within a sine inverse function. Okay, the way we've always dealt with these in the past is we've evaluated them from the inside out. So really, this problem is just going to be a 2-for-1. There's going to be 2 questions to answer in the same problem. Okay, so let's start off by figuring out what cosine of 7 pi over 6 is equal to. Okay, well that's just evaluating cosine, something we've been doing for months. So I'm going to go to my angles in standard position. I can convert cosine 7 pi over 6. Let's see here, I know pi over 6 is 30. So 30 plus 180 will be 210 degrees. So we're talking cosine of 210. So we'll go 90, 180, 210 will be somewhere around here. Now, one thing students always say is, how can I do that? I thought cosine was restricted to just the top of our coordinate system. Okay, cosine inverses, a regular cosine, a regular sine, a regular tangent can be anywhere. Okay, so I'm not doing an inverse right now, I'm just evaluating a cosine. Okay, we'll make our reference triangle. I know my reference angle here is 30 degrees. So I've got a 1 across from that, which will be negative, a root 3 adjacent to it, which will be negative, and a 2. All right, so cosine of this reference triangle would be adjacent negative root 3 over hypotenuse 2. Okay, which means when I say sine inverse of cosine of 7 pi over 6, that's the same thing as the sine inverse of this negative root 3 over 2 we just found. Okay, so I'm replacing the cosine of 7 pi over 6 with what I evaluated it as, this negative root 3 over 2. Okay, so that's part 1, and then step 2, we'll just do this sine inverse the same way we did a minute ago. Let's say that that's equal to some value x. Sine inverse of negative root 3 is equal to some angle x. And that means the same thing as the regular sine of x is equal to negative root 3 over 2. So again, we'll go to our angles and standard position. And this time, since I'm talking about an inverse, I am restricted to certain parts of the coordinate system. I do have to stay between negative pi over 2 and pi over 2. And if I want sine to be negative, that's going to be down in this fourth quadrant. So we're opening down. Sine is opposite over hypotenuse, so we'll have opposite negative root 3, hypotenuse 2. And adjacent side 1. Okay, the angle we're talking about here is 60 degrees. So we could say that our answer then, our x, is 60 degrees or negative pi over 3, if I convert that once again. Okay, so that's the idea of working through a composition, just like any composition really that we've done before. Work from the inside out. Okay, evaluate the inside first, substitute that into our equation, then evaluate the outside. So really this is the 2-for-1, two problems at the same time. All right, let's do the same thing with b together, but notice b, the inverse is on the inside, the regular trig function's on the outside. Different order, but really doesn't have a big difference on what we're doing here. I'm still going to evaluate this from the inside out. So we'll start off with tangent of negative 1, tangent inverse of negative 1 is equal to x. Well, what does that mean? That means the same thing as tangent x equals negative 1. Okay, with this one, there's actually a couple ways to think about it. With this negative 1, there's a few different methods I can use to get that. Okay, I could go to my angles and standard position. I know the tangent inverse is restricted between negative pi over 2 and pi over 2. So if I want to get the negative 1, I'll have to be in the fourth quadrant once again. And I can think of this negative 1 as negative 1 over 1. So as in opposite sides a negative 1, adjacent sides a regular 1, and then the third side, the hypotenuse, has got to be a root 2. Okay, so here we're looking at my 45, 45, 90 right triangle. And I end up with x is equal to negative 45 degrees. And I'll just leave that in angles because I'm going to be plugging it back into a cosine function in a second here. Okay, now the other way I could think about this one is drawing a graph of my tangent wave. Okay, tangent was the one that increased from left to right like so. And we know that one cycle happened between pi over 2 and negative pi over 2. Okay, and that's the restrictions on my tangent inverse, negative pi over 2 to pi over 2. And I know this graph hit 1 half between 0 and pi over 2, which is a pi over 4, okay, which is the same thing as 45 degrees. Okay, so actually two different ways we can think about that one. When you get the nice values for tangent, the 1, the 0, or the negative 1, you can also use the graph of the wave. Or with the 1s and negative 1s, you could still use our angles and standard position. Okay, anyways, after all that, what we just showed is that when we're looking at the cosine of the tangent inverse of negative 1, that's the same thing as cosine of negative 45 degrees. Again, because that's what the tangent inverse of negative 1 is equal to. And then from there, we'll just evaluate cosine of negative 45 degrees. So I'll go to angles and standard position. I need a different color. Negative 45 is going to open down like this. So 45 degrees here. Okay, 1, 1, root 2. This would be a negative 1. All right, so my cosine would be the adjacent 1 over hypotenuse root 2. And if I rationalize that quick, root 2 over root 2, I end up with a root 2 over 2 for a final answer. All right, last thing I want to do quick is look at the special case of when I'm composing a function and its own inverse. Okay, so both the cosine and the cosine inverse here. Really, it's not anything different than we just did, but I do want to show you a shortcut that you could use and when you can use it. Now, if we're composing a function its own inverse, what we'd expect to happen is that the cosine and the cosine inverse would cancel out, and we'd think we'd get a negative 1/2. All right, what I want to take a look at is, does it work that way? I'm going to say in this case it does, but I also want to show you a case where it doesn't work. Okay, so let's go ahead and do this problem. Again, starting on the inside here, I want to know what the cosine inverse of negative 1/2 is. Let's say that's some x. That means the same thing as cosine of x equals negative 1/2. Okay, well, to do that, we'll go to our angles in standard position. I know the cosine inverse is restricted to the top part of the coordinate system, between 0 and pi. And if I want this to be negative, I know I'm going to have to be in the second quadrant because everything's positive in the first. So here's the x I'm talking about. We're talking cosine, so we have the adjacent side over the hypotenuse. So adjacent would be the negative 1, hypotenuse would be 2. We'd have a root 3 for the opposite side. So this is my 30, 60, 90 right triangle. I know I've got 60 degrees here across from the root 3. So then my x is 60 short of 180, in other words, 120 degrees. Okay, so we have the cosine of cosine inverse of negative 1/2 is the same thing as the cosine of 120 degrees. Okay, now from here, I can use the same picture. I've got the 120 drawn. I've got my reference angle. Cosine of 120 would be the adjacent over the hypotenuse. So just a negative 1/2 as well. And in this case here, the cosine and the cosine inverse did cancel just to give us this negative 1/2 here. All right, I'm going to say anytime you're doing a trig function with the inverse on the inside for the composition, you just get this answer out here. Let's take a look at when that doesn't work quick. All right, notice this time in part D, the inverse is on the outside, the actual function's on the inside. So this is where you need to be careful, because I'm going to say this one's not just equal to 2 pi over 3. And I know that right off the bat because we said we can't have anything for a tangent inverse that's greater than pi over 2. 2 pi over 3 is greater than that. So let's show you why I can't just say 2 pi over 3 with this one. Let's start on the inside of the function. Let's evaluate tangent of 2 pi over 3. And if I switch that to degrees, that'd just be tangent of 120 degrees. We'll graph that out. 120 is going to take us to the second quadrant. All right, which will give me a reference angle of 60. We're talking 30, 60, 90, so I have a root 3, a 1, and a 2. This would be a negative 1 here. All right, so I could say that tangent of 2 pi over 3 is the same thing as tangent of opposite over adjacent. We could say negative root 3 over 1. And whoops, we want the inverse. And the reason this isn't going to just be the 2 pi over 3 is, again, let's say that's equal to x. That tangent inverse is equal to x. Means the same thing as tangent of x is equal to negative root 3 over 1. And when I go to solve this part of the problem, The issue I have here is that my tangent inverse is restricted from negative pi over 2 to pi over 2. Okay, I can't be in this second quadrant. I can't have an answer here. I've got to make my answer in the fourth quadrant. So I run out of room here. So opposite negative root 3, adjacent 1, hypotenuse 2. This would be my 60 here. So really what we're talking about is that x is equal to negative 60 degrees, or x equals negative pi over 3 if I convert that. Okay, so as far as that shortcut goes, if the inverse is on the outside, we can't just cancel things out if my angle falls outside of the restrictions on the inverse function. Okay, to sum that all up for you, sine inverse, or sine of sine inverse, cosine of cosine inverse, and tangent of tangent inverse of x is just equal to x for all values of x. But if I do that backwards, sine inverse of sine of x equals x, cosine inverse of cosine of x equals x, and tangent inverse of tangent x equals x, only when x is in the domain of the sine inverse, cosine inverse, tangent inverse. Okay, if it's outside of that domain, if this angle on the inside is outside the domain, we'd have to do things by hand like we did a second ago. Okay, that's something that's nice to know. It's not something you have to know. A common thing for the ACT to throw at you, though, is a problem like this where you can just cancel and use that shortcut, okay, to increase speed, basically. Or they'll give it to you to see if you know when not to cancel. Okay, so it's good to know. You will see a couple in the homework where you could utilize this or maybe not. If you're uncomfortable with using the shortcut, just work them out by hand like normal, and you'll get the right answer that way. All right, so that's it for section 5.1. It did take us a while to get through this video today just because there's a lot of details we had to talk about. But hopefully you'll realize as you're going through the homework that as I actually get into these problems, they don't take that long. They're not that bad. They're kind of just the same thing we're doing in part 1. Okay, so give the homework a shot, get that finished up. Let us know if you need help. We'll be here to help you out.